Hello everyone, welcome to Equal To, and this is the first video of our number system playlist. And if you haven't watched the previous videos yet, please go and check them out. I'll give you a link. If you have seen those videos, we are going to continue with that. Now in the previous video, we saw what irrational numbers are, and we saw how to plot root 2 and root 3 on a number line. We have seen both those things. Okay. Now with that, the example section of that portion is over. Now we are moving to the exercise questions of this portion. Okay, now this is exercise 1.2 of chapter 1 number systems, and the first question is state whether the following statements are true or false. Justify your answer. Okay, now that is what we are going to do now. The first subdivision is every irrational number is a real number. Okay, now for you to answer this question, you need to know what real numbers are. That I haven't told you yet. Okay. Now, in the previous video, we saw what irrational numbers are, right? And the video before that and the one before that, we have seen what rational numbers are. Now, real numbers is just a collection of both rational and irrational numbers. Okay. Real numbers is irrational plus rational. Okay, now combined together, this is what we call as real numbers, and the symbol for real numbers is R. Okay, with capital R, with uppercase R, we represent real numbers, and real numbers is a collection of irrational and rational numbers. Now we have drawn number lines, right? And we have also marked both irrational numbers and rational numbers on number line. For irrational numbers, we have marked root 2 and root 3 in the number line. For rational numbers, we have marked so many things. -1, integers, fractional numbers, positive numbers, everything. We have marked everything in rational numbers. So both irrational numbers and rational numbers can be marked in the number line, and that is why we call it as real number line. Okay, so the number line can also be called as real number line, not line, it's line. Okay, real number line. So this is what real numbers are. Real numbers is just a collection of both irrational numbers and rational numbers combined together. So I'm just going to rub this on, and we are going to move on to this question. I hope you know all the things that is required to answer this question. Every irrational number is a real number. Of course, it's true. We just saw it. T-R-U-E. True. Okay, why is this true? Real numbers is just a collection of irrational and irrational numbers. Combined together, it's called as real numbers. So, obviously, every irrational number comes under real numbers. I think it's quite obvious, and it's a very easy question. Okay. I'm sorry. I went back a few pages. Okay. Now the second point. Every point on the number line is of the form m, where m is a natural number. Now we have to note that they are telling m is a natural number, and every point on the number line is of the form m. Obviously not. In a number line, it's obviously called a real number line. We have just saw it. So in a real number line, you can plot irrational numbers, rational numbers. And natural numbers are just a very small portion of, in fact, it's the smallest subset of rational numbers. Okay, it's the very small one. We saw a diagram right in the first video, right? I hope you remember that. Now in that we saw natural numbers are the smallest ones, and when we add 0 to natural numbers, we add whole numbers, and that is how we will build up entire thing. And real numbers are very high at the top, which includes rational and irrational numbers. Okay, now we know all these things. All of real numbers can be plotted in a number line. So obviously every point in the number line is not a natural number, because it can be any number. Okay, so this one is false. Okay, now moving on to the third question. Every real number is an irrational number. Now that also is false, because real numbers include rational numbers as well. Rational numbers plus irrational numbers combined together is what we call as real numbers. So only irrational numbers cannot be real numbers. Okay, so this is what this question is all about. I hope you understood these things. Well and good. Moving on to the second question of this exercise, which is, are square roots of all positive integers irrational? If not, give an example of square root of a number that is rational number. Okay. Now, we know root 2 is a positive integer, right? Sorry, 2 is a positive integer. But root 2 is irrational. Now, with that, can you say every positive number's square root is irrational? Absolutely not. You cannot tell that, because let us consider 4 for example. 4 is a positive integer, right? 4 is a positive integer, and square root of 4 would give you 2, right? To be precise, it can be plus 2 or minus 2. It can be both, because minus 2 squared is also 4, plus 2 squared is also 4. So it can be plus 2 or minus 2, but in either cases, both these are integers, right? Both plus 2 and minus 2 are integers. These are not irrational numbers, these are rational numbers. Integers come under rational numbers. So any positive integer's square root is obviously not irrational, and that 4 is a very good example to display that. 4 is a positive integer, and square root of 4 can be either be plus 1 or be either be plus 2 or be minus 2, and both these numbers are just integers and not irrational numbers. So integers are obviously rational numbers, and hence this is an example and this statement is false. Okay, square root of all positive numbers irrational? No, that is not true, and this is an example to prove that. Okay, I hope you get this. Now moving on to the third question. Now the third question is very similar to the examples that we saw in the previous video. Okay, you are supposed to mark root 5 in a number line. You are supposed to represent root 5 in a number line. So before doing that, you just have to express root 5 first in terms of a sides of a triangle. Okay, so I hope you have seen the previous video. We have seen that in detail with an example. Now we are going to use the same concept, so go and watch that if you haven't watched that yet. Now we are going to have a right angle triangle, and that is how we are going to get root 5. Okay, we are going to have a right angle triangle, and that's hypotenuse is going to be the value root 5. Now to have root 5 as the hypotenuse, what should be the dimensions of the sides of a triangle? Okay, so that is a very simple question, I think. Now root 5 is equal to, you can have 4 plus 1 as 5, right? 4 plus 1 is going to be 5. And is there any other way that you could express root 5? There is a lot of other ways, where it could be what do you say, 3 plus 2, okay, or it could be 2 plus 3, which is exactly the same, or 1 plus 4, which also is same as the other one. Okay, now these are two ways you can express. Now if you express it in the Pythagoras formula itself, how it would be? It would be 2 squared plus 1 squared in case of 4 and 1, and it would be root 3 squared and root 2 squared in case of 3 plus 2. We know we need this, right? We need these to draw this triangle, and only then we will be able to get the hypotenuse. So we need to construct 2 and 1, or in this case root 3 and root 2, in order for you to get root 5's dimensions. Okay, now root 2 and root 3, they are hard to construct, they involve a lot of steps, whereas just drawing a line of size 2 is quite easy. Now, so that is the approach that we are going to take. So which is the approach that we are going to take? This one, the first one, that is what you are going to take. So how are you going to do that? we first take a number line. Okay, and I'm just going to mark 0 here, 1. I'm doing this mistake again and again. Sorry, please don't mind me. So 0, 1, 2 and 3. Right, let me just have -1 as well. It doesn't matter, but we have. Okay, now for root 5 to be the hypotenuse, one side should be 2, another side should be 1, right? 2 plus 1, and that gives you the hypotenuse. So one side should be 2, another side should be 1. Now let us take this as the 2 side, okay, and we are going to construct a 1 here and obviously get a hypotenuse. Okay, now you might think I'm going a little fast, but these are things that we have already seen in the previous video and you are quite familiar with these things. We have drawn root 2 and root 3 as well in the previous video. So you are going to just use the same procedure. It's very simple, and let me just mark these things OA and B. Now OA is equal to 2, AB is equal to 1, and hence using Pythagoras theorem you can say that OB is equal to root 5. In this case this would obviously be root 5. Now how are we going to transport this to the number line? We need, because this is the number line, this is not the number line, this is at an angle, but we need it on the number line. So what you're going to do, you're going to take a compass with its needle placed at O. You're going to measure OB and you're going to draw an arc here. Okay, taking a compass, having its needle at O, measuring OB, and you're going to draw an arc so that it cuts the number line. And the point that it cuts the number line, that is going to be root 5. Okay, that is going to be root 5, and that is how you plot root 5 on a number line. Okay, I hope you understood this. Now this is the same procedure how we used to draw root 2 as well. We have seen that very clearly in the previous video. We are just going to construct a triangle with 2 and 1 as its sides, and its hypotenuse would give you root 5. Using that measurement, just going to cut in the number line, and that would give you root 5 on the number line. Okay, that is all the questions for this video. I hope you understood these things. If you have any doubts, if you have any questions, please feel free to put them in the comments. I'll get back to you as soon as possible. I hope you liked this one. Thank you so much for watching. See you in the next video. Bye for now.